Hello, Gen Chem Nation. We are now talking about radioactivity, really now nuclear reactions. And so now we're getting basically into the chemistry of the nucleus. So we're really now actually talking about changing one element into another. Because if we change the number of protons in the nucleus, we change the element. So we're finally disobeying the laws set down by Dalton, right? Remember Dalton's atomic theory. So we're really not playing around with the actual nucleus. And so just to remember that we have, kind of a general way of writing these. We talked about this a very long time ago, right? But we have this idea of, chemical symbol. And because we're talking about transferring or transmutating from one element to another, that's why we also need, this idea of atomic mass. Remember, this is really the number of protons plus the number of neutrons. And then we have Z, which is our atomic number. And so the atomic number is the number of protons that we actually have. So with all of this, we can actually figure out, number of protons, number of neutrons, and number of electrons. It's a very old topic for us in describing, an atom or an element and how we can characterize it. Remember, the atomic number is the piece that really defines the element. While we could say atomic mass would be something that more defines the isotope of the actual element. So that's what we're going to get into with looking at now nuclear chemistry and radioactivity. So let's start historically. And not too much here. We really have first Becquerel. Becquerel is, one of these old dog chemists. Back in the day, it was really a lot of old white dudes. And so Becquerel did a couple of different things. Becquerel did win the Nobel Peace Prize. For his efforts. But as far as nuclear chemistry goes, he discovered uranic rays. Basically serendipitously. And that means really by chance. He was lucky. But also, he, understood the scientific method. With that notion of, observation and experiment. So Becquerel noticed when he was working with some uranic rays, he was actually working uranic rays. He was working with basically uranium sulfate. So that was the particular, just salt, I guess you if you will, he was working with, and he observed the development of photographic plates. In an environment that had no light source. Basically, photographic plates in a drawer with, by chance, a rock of uranium sulfate. So that's really the observation, and just to show that maybe pictorially, right, we could look at the actual rendition of it here with, the idea that we have a photographic plate, and we have the uranium sulfate, which is the brick or the rock that's on top of the photographic plate. And then we just look at the photographic plate, we actually see an image, or we see development. So that means that something had to have been happening here as far as the fact that, well, in order for a plate to be developed, it needs to be exposed by some type of radiation, such as light or X-rays or what have you. That was really Becquerel's really interest was in this idea of X-rays. So he put together that there was then some type of radiation that was being produced by the uranium sulfate. So something was developing the plate from the rock. And so this new light, as we could call it, emanated from the uranium sulfate solid. And that's where the notion of uranic rays comes into being. So that's Becquerel. Becquerel had a postdoc who we all recognize as Madame Curie. And to be honest, this is, as far as historically, is very strange because women did not have a major role in society back then, especially in science. It's pretty much an old white dude's game, sadly. But Curie broke down a lot of those barriers. And so here we have, Madame Curie. And basically what she did is that she discovered this idea of, uranic rays, was basically a property found in other elements. And she basically found many, as well as discovering some on her own. For instance, two of note would be, polonium. Polonium name comes from that, she is from Poland. Another one is radium. This rock actually glows in the dark. Something very menacing about that idea. As well as curium and some other things that she didn't necessarily discover, but she gets a lot of, a tribute, kudos, if you will, for her expansive look into this notion of radioactivity. And that's really what came about, is that, since this uranic ray is, common to more than one element, right? The term radioactivity is basically born. And so that's all because of Curie. Radioactivity can be divided into several pieces. With radioactivity, basically you have an unstable nucleus or a radioactive nucleus. And that's going to emit certain types of particles, certain types of light, right? And that's what Becquerel was observing, right? He was observing light that was developing his photographic plates. So we find that now there's, multiple ways that these radioactive nuclei or unstable nuclei can emit this type of radiation. And so we have first our alpha particle. That's given the denotation of the alpha Greek letter there. We have beta particle, and beta tends to get this type of moniker. We have gamma, radiation. We could talk about that in Bruce Banner and the Hulk in a little bit. We have positrons. And we have K capture, or electron capture. These are the 5 different modes of radioactivity that we're going to talk about within this particular lecture series. There are more, but these are the main ones that we're going to get into. Radioactivity as well is a first order process. And so that means we need to remember kinetics as far as that when we look, or when looking at a nuclear reaction, the kinetics are governed by first order kinetics. And so that means, you might recall that we have that notion of half-life, along with that how long it takes for the concentration to decrease by 50%. And then we also have the notion of the linear plot, where we would have the natural log of a concentration of some component at time t is equal to negative little k times t plus the natural log of that initial concentration. So that's kind of the intro with radioactivity and nuclear chemistry. Historically we got Becquerel and Curie. Curie doing a lot of work in that area. Definitely Curie and other players with this idea of radioactivity didn't realize the dangers, and so there was a lot of radiation poisoning and subsequent death, which is unfortunate that they are pushing the level of chemistry, if you will. And subsequent lectures we'll get into now looking at, these different types of particles. Now let's look at balancing. Nuclear reactions. We cannot balance by element due to, the nucleus, or due to the nuclear process. We balance now by atomic mass and atomic number. The sum of the atomic mass on the starting material side should equal the product side, and the same is true for atomic number. So we have to balance out these numbers now, as opposed to elements. So let's look at an example here of taking sulfur 32 and hit it with a neutron to produce something as well as a proton. So we have our sulfur 32, neutron, proton, and what we're really trying to determine, which is that box. So, first balance out atomic mass. We have, basically, if we look at the atomic mass on our product side, that's equal to 33. And the atomic mass, that 33 is the atomic mass on the starting material side. And the atomic mass on our product side is 1. So that means the missing mass is equal to 32 for the unknown. So we have one piece of that puzzle, so we could, write the reaction again just to throw that into the method. I think you'll find this type of balancing isn't too terrible. that here's where we would be now in that process, and we can see that our numbers are actually equal to one another as far as mass. We have a mass of 32, or I apologize, 33, and we have that same mass as well. So now the mass is balanced. And so now we can go to the charge, if you will, or balance out or number of protons. We have, as far as our number of protons in our product side, we have a total of 16. Again, I apologize, I get that backwards. That's our starting material side. Number of the protons on our product side is only equal to 1. So the missing number of protons is equal to 15. And that would be for, again, the unknown that we're looking at. So now we can develop that reaction to be pretty much balanced by mass and by number of protons. And so now we can look up element with atomic number equal to 15. And that would be looking at phosphorus as our element. So that would be balancing of a nuclear reaction. Another example, maybe a little bit faster here, would be to look at magnesium 24 reacting with something in a nuclear process to produce silicon 27 and a neutron. So we can just balance out, these different processes, right? We have our atomic mass here equal to 24, while here our atomic mass is equal to 28. So we would expect a mass of 4, and our atomic numbers here was equal to 12, while our atomic numbers on the right was equal to 14. So we'd expect something with an atomic number of 2, and that means we have helium as our other starting material for this particular nuclear process. Again, all we're doing is adding up the starting materials and their atomic mass, taking that with the difference of that in the product, and the same with the atomic numbers, and then we end up with this as our final balanced process. So there's our balanced reaction. The same method basically applies to decay reactions as well. And so a decay reaction, you're really just looking at one element turning into another element. So we had cesium 142, and it was turning into barium 138. Right? We would expect that element to have, or that particle in the decay process, to have an atomic number of 4, atomic number of 2, and so that would be a helium or an alpha particle that's produced in that particular process. Or if we had, let's say, cerium 131 undergoing, these types of decay processes to produce lanthanum 131. Well, we'd have to balance this out. We would have something that has a mass of 0 and has an atomic number or charge of 1. And that is our positron type particle. We'll talk more about those types of decay particles in a subsequent video. There's also stepwise decay processes. And these are ones that occur by more than one of decay process. So, as an example, we could look at uranium 238 going to lead 206. Right, this occurs by both alpha and beta decay. How many alpha and beta particles are produced in this decay? So for this type of process, if we look at the particles individually, we have our alpha particle, which is really a helium atom, and we have our beta particle, which is really, an electron. So they both have mass, or rather they both have charge, but only the alpha particle has mass. So that is your starting place. if we look at uranium-238 going to lead-206, we see a difference in mass of basically 32. And we know each helium atom or alpha particle has an atomic mass of 4. So if I take my 32 and I divide by 4, I end up with 8 alpha particles. So I can rate now a little bit more to this stepwise decay. Where now I know the number of alpha particles, right, based on that change in atomic mass. And only alpha particles have the mass. So now, the number of beta particles is basically based off the atomic number or charge balancing that needs to happen. So we have, in terms of our starting material side and atomic number, we have a sum of 92. But if we calculate how much we have on the product side with atomic number, we have 98. So that means we need 6 beta particles to balance out the actual charge. So our reaction would look like this now. Where now we have everything balanced. We have our sum of 238 balanced out as well. If we add up all those masses, we get 238. And if we then add up all the atomic numbers or the charge, we also get 92 on both sides. So our stepwise decay reaction is now balanced from uranium-238 going to lead-206, produces then 8 alpha particles and 6 beta particles. So that's our balanced reaction, and that's balancing of nuclear reactions in general. whether they be decay processes or simply nuclear reactions.